Hello and welcome to lecture 33 of the course Computational Complexity. So far in this course we have seen time-bounded complexity classes, space-bounded complexity classes and randomized complexity classes. In this lecture we are going to introduce a new model of computation called circuits, and in the upcoming lectures we will see computational complexity classes which are based on the circuit computation model, right? So circuits are a rather standard form of computation, even though we are seeing it a bit later into this course. Right? It's a very simple, very intuitive form of computation. Right? So it's like Boolean formulas generalized into a computation model. Right? So I'll first quickly explain why, very briefly, the motivation for the circuit complexity model, why people began to study it, and what were the reasons, what are the motivations, before explaining the model itself with a few examples, right? And we will not formally define the model in this lecture, but we will see a lot of examples. So in 1982, there was a paper by Richard Karp and Richard Lipton, where they made the following quote. Right? They said that one might imagine that P is not equal to NP, but SAT is tractable in the following sense. For every L, there is a short program that runs in time L squared and correctly treating all the instances of size L. Right? Meaning, it could be the case that SAT is not solvable in polynomial time, but given all the instances of a certain size, right? Let's say if for a fixed size instance, fixed size formula, maybe there is a way to solve it. Right? And this way may not be a general approach. So for a certain L, there is a fixed way. For a different L, it's a different way. But and even coming up with the way may not be straightforward. So because of which you cannot get a polynomial time algorithm that applies to all the problem instances, all the sizes, all the problem sizes, right? So this is basically a motivation to consider what is called a non-uniform model of computation. Can we have algorithms or ways to decide different size instances differently, right? And circuits are a computation model where we can do the non-uniform computation, right? So in other words, can we have different algorithms for different problem sizes, right? And this is one motivation, and this is this because of this reason, right? People have studied. This was one motivation to study the circuit complexity model rather than the Turing machine model, because in a way to resolve P versus NP, people thought that because of this peculiar property, maybe circuits are the way to go, and people tried various approaches using the circuit computation model. However, it was later shown that it is unlikely that even this question is going to be true. The same question that Karp and Lipton have asked here, it was shown that this is unlikely to be true, right? Because if this was true, something else unlikely happens, right? However, this was a initial motivation to study circuits. Perhaps this was the way to go, and this distinction may help us resolve P versus NP, right? And Turing machine, even though we started with Turing machine in this course and we consider it equivalent to our everyday computers that we see, however, it's still a rather complicated model. So you have a tape that runs around, you have this tape that reads and then moves right or left and then erases, rewrites, right? So this is a rather involved, intricate model. Whereas, as you will see, circuits are very, very simple, straightforward model, right? So perhaps it may be easier to study a simpler model. Perhaps this may lead to an easier resolution for P versus NP. This was another hope, right? And until now, lots of people have worked on P versus NP using the circuits, but still there has not been much success, right? Another reason for studying the circuit complexity model is the fact that this captures the notion of parallelism in a nice manner, and that is one reason why this may be good to understand. So this is a third reason why circuit computation model has been studied, right? So these are the motivations, and we'll first start, as I said, with just one language, and we will see different ways to realize that language, right? So this is what we'll start with. Okay, and that will give you an idea of what circuits are before going to the formal definition, right? And I'll just briefly describe what they are, so that you have some context, and we'll formally define it in the later lectures. So circuits are directed acyclic graphs. So they have direction, they have graph without cycles, where you will have many inputs, let's say n inputs, and a single output. So in the directed acyclic graphs, there will be sources and sinks. Sources are vertices that do not have incoming edges, and sinks are vertices that do not have outgoing edges. So in this we have n sources and one sink, and all the non-source vertices are a logic gate like AND or NOT, right? So we'll use this symbol to denote AND, and this symbol, the V symbol, to denote OR, and this symbol to denote NOT, right? And what I'm going to describe is one language and different ways to realize that language using the circuits, right? And in fact, this lecture is most of this material for this particular lecture and the next lecture, where I think I'll move on to, is from if you search online for IARCs and computational complexity theory by Professor V. Vinay, right? If you Google for IARCs, computational complexity theory, and V. Vinay. IARC stands for Indian Association for Research in Computer Science. It's an old association. There is a bunch of lecture notes that you will get by Professor V. Vinay, and this is the first lecture of that course, right? So that's one reason, it's a very nice example to illustrate the circuit complexity model. So again, you'll find the same things, but anyway, I will also provide you with these notes. Okay. Right. So what is the language that we are going to consider? The language that we are going to consider, in fact, it's a family of languages called n subscript n superscript k. So TH stands for threshold. So this is the set of all n bit strings, n bit 01 and n bit strings that have at least k ones. So this is a set of all n bit strings that have at least k ones. So just to understand this, we will see some simple examples. When k is 1, this is the set of all n bit strings that have at least 1 1, right? In other words, it's just the OR function. And when basically at least one of the x1, x2, x3 up to xn has to be, at least one of them has to be 1. So this will be 1 if this will be in the language. So if at least one of them is a 1. Threshold nn means that of the n bits, there has to be at least n of them have to be ones, which means all of them have to be ones, which means it is the AND function, right? All of them have to be ones. And next is when k is n by 2, right? So half the bits have to be ones. In other words, it's what is called the majority function. So at least half the input bits have to be ones. So when n is odd, this is the actual majority. When n is even, it's kind of like the majority, right? Half of them have to be ones, right? So this is sometimes called the majority function. And what we will see is from this threshold family, we will see the language threshold n with k equal to 2. Okay, so x1, x2 up to xn are the individual bits, right? These are the individual bits, and the strings in the language are those strings that have at least 2 ones. Okay, set of all x that have at least 2 ones. Okay, and maybe you may want to ask, how would the Turing machine compute this, right? So you could just write a simple Turing machine algorithm that just scans the input from right to left and just looks for 2 ones, and once it sees 2 ones, it can just stop. Right, so this, it just needs so all it needs to remember is whether it has seen at least one, right? So that it can be just 1 bit flag, and of course it also needs to, it doesn't even need a counter, right? It can just go 1 1 1, like one step, one cell to the right till it hits the end of the string. It doesn't even need a counter. So all that it requires is order n time. So if you have a Turing machine, there is a order n time. This is an n. Sorry if you are not able to read my handwriting. Order n time and constant space algorithm. Right, this is a standard thing. Anyway, what we are going to see today is not Turing machines but circuits. And we will see, again, as I said before, we will see circuits using for threshold n threshold 2 using AND, OR and NOT gates. Okay, so this OR is written like a V, AND is written like a wedge. It's called a wedge, but it kind of looks like an A without the horizontal bar, and NOT is this. Right. And some of the interesting parameters, right? So later we will see complexity classes for the circuit computation model. Just like we studied time and space in the Turing machine model, some of the interesting parameters to measure are size of the circuit. Size of the circuits are just the number of logic gates that are used in the circuits. The number of wires of the circuit, so number of wires, you will see what they are when we with some examples. And fan-in, again, fan-in means what is the maximum number of inputs any gate can take. Okay, this is what is called fan-in. Again, size and fan-in you may have heard when you study digital logic in your undergraduate, right? So let's try to understand, let's try to realize this function threshold 2 using some circuits, right? So the first approach is what is the brute force approach, right? So we are saying that out of the n bits input, there is at least there are at least 2 ones, right? So why not have a very simple idea? Try all possible pairs of input bits. So like here I have drawn it for 4-bit input, right? x1, x2, x3, x4, and basically I have there are 4 bits, right? 4 input bits, so n input bits, and I have basically n choose 2 AND gates. So because it's 4, we have 6 AND gates. Basically all possibilities, x1, x2, x1, x3, x1, x4, then x2, x3, x2, x4 and x3, x4. 6 possibilities with the 4 inputs. So in general it is n choose 2 AND gates. Okay, maybe this is not very visible. I'll write with another color. N choose 2 AND gates, right? And if there are 2 ones in the input, at least one of these AND gates will give us a 1, right? If there are 2 ones in the input, xi and xj be the input, so there will be an AND gate which takes xi and xj as input, and that will report a 1, right? And so we finally have an OR gate, right? We finally have an OR gate to check if is there any AND gate that is reporting a 1 or that is reporting true, right. So this is, or just a bit more formally, we have the AND gates between each pair is called Gij, right. So which is an AND between Xi and Xj, and the circuit is just an OR between all the Gijs. So suppose there are two inputs I and j for which Xi and Xj for which Xi and Xj are both 1, then Gij will fire, meaning Gij will report true, which means the OR gate will also report true, and this the stop gate is the output gate, and that will be we'll try to illustrate the output as well, right. So let us see how many gates we have, right. How many gates do we have? So we have 6 gates here, 6 AND gates and 1 OR gate. So 6 is n choose 2. So we have n choose 2 AND gates, right, n choose 2 AND gates and 1 OR gate, which is, so n choose 2 is like n into n minus 1 by 2, so it's order n squared. So number of gates is order n squared. Number of wires, so number of wires is just how many wires are there, right. So let's say each input going to one of the gate and each gate going to another, or each output of a gate going to another gate's input, right. So let us see, each input Xi or X1 goes to 3 gates here, that is because X1 is involved in, it has to be compared with each other, right. So or another way to check is there are n choose 2 gates and each takes 2 input wires. So n choose 2 into 2 is the number of wires to the first level of gates, and above there is an OR gate that takes again one input, n choose one input from each of these AND gates, so that is n choose 2 wires. So this is the n choose 2 wires are for the inputs to the OR gate. So 2 times n choose 2 for the AND gate and n choose 2 for the OR gate. So total is 3 times n choose 2, even that is asymptotically order n squared. So both number of gates as well as number of wires is order n squared. And fan in is the maximum number of inputs that any gate has. So here all the AND gates take fan in 2, but the OR gate has fan in n choose 2, right. So the AND gates have fan in 2, but the OR gates have n choose 2, and n choose 2 is what we call unbounded, meaning the number of inputs or the fan in for that gate is actually dependent on the input itself, meaning that if n is bigger, then the fan in also will be bigger, but the AND gates it's always 2, so it is fixed, whereas the OR gate it is unbounded. When the input increases, the number of inputs to the OR gate increases. So that is what we call unbounded fan in. And in circuits, right, so as you may have imagined already, it is desirable to bring down each of these parameters, right? Gates, wires, fan in, it's better to have smaller of each of these, right. These are all resources and we want to be economical in using them, right. So we saw the brute force approach, which uses n squared, order n squared gates, n squared wires and unbounded fan in. Now let us consider another approach called which we will call the recursive approach, right. So what is the recursive approach? So if there are two, again if there are so we want to check whether there are two input bits Xi and Xj which are both 1. So now consider right, so x1, x2, etc. xn divided by 2 and then xn divided by 2 plus 1 up to xn. So there are 3 possibilities. Either there are 2 ones in the first half, x1 to xn by 2, or there are 2 ones in the second half, xn by 2 plus 1 to xn, or each half has only 1 but then each half separately has 1, right. So there are 3 possibilities by which you could have 2 1s. So if the first half has a 1, we could use a recursive formula. So that's what we are trying to implement here. So in the left half, right, we are trying to implement, if basically we are using the same circuit, a smaller instance of the same circuit. We are using a threshold realization which takes n by 2 bits, right? And similarly in the right side we are again using a threshold realization which takes n by 2 bits. However, there is a third possibility that is there is 1 1 on the left side and 1 1 on the right side. So in order to realize that, we have to basically check, is there a 1 in the left side and if there is a 1 in the right side, and if both of them are there, then we can say okay. So we have an OR gate here and we have an OR gate here. Basically this OR gate will fire if the one on the left side, this will fire if there is at least one on the left side, and this OR gate, the right side one, will fire if there is at least one on the right side, and if both of them fire, we are okay, right? So we just want to check if both of them will fire, meaning there is one on the left and one on the right. So this is, and this can go as input to the top level OR gate. So there is a recursive implementation for threshold over n by 2 bits on the left and the right, and then there is this red part which is the verification of whether there is one on the left and one on the right. And at the end we are just taking an OR gate, and this is the output. Right. So this is the basic idea. And what is this number of gates here? So just like you might have done recursion or recurrence relations in your undergraduate algorithms, now we need to see, so how many gates do we have? We have one top level gate, this one, and we have 3 gates over here, the red part, so that is 4 gates. But then we have these 2 recursive components. This is basically the threshold function itself implemented recursively. So again we will have similar structure in the threshold part, right? So basically the size is 2 times the size of n by 2, right? So this is threshold function for an n by 2 sized input. So 2 times the size of n by 2 plus the 4 gates that I marked, right? So I am erasing this, plus the 4 gates that I marked. So 2 times size n by 2 plus 4, and this is something that you may have solved in an undergraduate using the standard master's recurrence theorem, and this turns out to be a linear, right? So this is linear order n if you solve this recurrence. So this is not very difficult to see, you can just try solving it yourself. This may also help you brush up how to solve recurrence relations. The number of wires, okay, so there are n by 2 wires going into the left threshold, there are n by 2 wires going into the right threshold, there are n by 2 going into this OR gate, in the left OR gate, there are n by 2 going into the right OR gate. So n divided by 2 times 4, so that leads to 2n wires over here. Then there are 5 wires, so which I will mark with green. There is 1, there is 2, there is 3, there is 4, there is 5. There are 5 wires extra. So 2n plus 5. And then there are whatever wires are there inside each of these threshold n by 2 gates. Right. So 2 times wires of n by 2, which is basically the recursive call. And if you work that out, you will get order n log n. In fact, if you work this out, you may get n log n, but there may be a bit of overcounting here, because you may be counting the same wire that is going out of this x1 x2 inside as well, but still I think you will get order n log n. Again, this is something that is standard recurrence solving, that you can work it out. So now from n squared and n squared gates and wires, so this one is the number of gates is size, right? N squared and n squared. Now we have n and n log n, right? and the first one had unbounded fan-in, whereas this one also seems to have unbounded fan-in. But there may be a way to reduce the unbounded fan-in. So for instance, this red OR gate, right, the one that I have circled, that takes n by 2 fan-in, right, whereas the other gate, the top level OR gate, takes 3, then the AND gate takes 2. But however, notice that inside these threshold functions, inside the recursive calls, you will have other OR gates which you may be able to combine to get the OR gate over here. So you may not have to actually implement an OR gate with n by 2 fan-in or at the top level. So what I'm saying is, if you expand this threshold n by 2 gate, right, you will again find one OR gate that takes n by 2 plus 1 to 3n by 4. So I'm expanding the right side threshold gate, and then another OR gate which has 3n divided by 4 plus 1 to xn. Okay, so I've left omitted the superscripts. Right, so it's xn by 2 plus 1 to x3n by 4 and x3n by 4 plus 1 to xn, and this would already be implemented in this threshold gate. So all you need to do outside for the OR from xn divided by 2 plus 1 to xn is to just take the OR of these two, right? So OR of these two, right? So you could just bring it out and take another OR, right? This is something that you can do. I'll just erase this part, and so you may not need an unbounded fan-in, right? So I'll just leave a question mark. So it is not really unbounded fan-in. If you want, you can implement it with a bounded fan-in. Bounded fan-in meaning fan-in 2 or 3 or something like that. It will not vary based on the input. Okay. The third approach that I want to consider is what I will call the hiding approach. Okay. Again, all of these are interesting and clever in their own ways, right? So we have two approaches seen already. One where size and wires were both n squared. The second where size was n and the wires was n log n. The second we said had bounded fan-in. Third one is what is called hiding approach. So again, the question is this: are there two xi's which are both 1, xi equal to 1, xj equal to 1, right, where I not equal to j. So if there are two such xi's which are both 1s, then even if we hide one of the xi's and take an OR of the remaining bits, it should still give us 1, because there are at least two 1s. So even if you hide any input bit, the OR of the remaining things should give us a 1. And this will happen only when there are two input bits equal to 1. If there is only one input bit equal to 1, then if you hide that, the rest of them will not give an 1 upon ORing them. So what we do in this approach is to simply take all the possible there are n input bits. So you hide x1 first, then you hide x2 first, then you hide x3 first, x3, and so on till finally you hide xn. And for all of this, once you hide x1, you take the OR with the remaining bits. Then you hide x2, you take the OR with the remaining bits, and so on. And then finally you check whether all of these are 1. If all of these are 1, this means that there are two 1s in the input. Okay, so you have ORs at the bottom level and then an AND at the top level. So first I have, so maybe I'll just write the x1 here, which I have hidden, then x2 I have hidden, and then x3 I have hidden, and finally xn is being hidden, right? So x1, x2, xn, so this smudging indicates it being hidden, right? And we are taking an OR of all the input bits except, so I'm looking at this one, we are taking OR of all input bits except x1 in the first part. And similarly, we are taking OR of all input bits except x2 in the second part, and so on till the OR of all bits except xn in the last part. right? And what we really want to know, what we really want to do after this is to take an AND of all the ORs. So we have an AND of all the ORs. Okay, so right, so this is the output. So what is the size here? The size here is I have written n here, which is not quite correct. So there are, okay, there are so how many x1 can be hidden, then x2 can be hidden, then x3 can be hidden. So there are n OR gates at the bottom and plus one AND gate. So it's actually n plus 1. Right? The number of sizes is the number of gates. There are n OR gates and one AND gate. And the number of wires, again this is not very difficult to see. Each of the OR gates has n minus 1 inputs. So n times n minus 1 plus the AND gate has n inputs. So that is n plus n. So n times n minus 1 plus n, which is n squared. So size is n plus 1 and fan wires is n squared. The fan-in is unbounded, however, because both OR gate and AND gate take n minus 1 or n inputs, which obviously varies with the input size. So fan-in is unbounded. Again, this is, so we saw the recursive approach, which took order n size and order n log n number of wires. This one takes linear size and n squared wires, quadratic number of wires. So again, this is not that great, but it's a simpler construction. Okay, so I believe I have 3 more approaches, which I think I will cover in the next lecture. So just to summarize this lecture, I introduced what is the circuit model of computation, right, and the motivations explained. Then explained what is the threshold function, threshold k function, and what we will see we saw in this lecture was threshold 2 function, and we saw 3 approaches: the brute force approach, the recursive approach, and the hiding approach. And we saw the size, number of wires, and the fan-in of each of these approaches. And just to reiterate, these the parameters like size, wires, fan-in are standard measures of measuring the circuit complexity. So just like we saw time, space, etc. in the case of Turing machine model, these are the parameters that are considered for the circuit complexity model.